Hey everyone, so this video talks about applications of derivatives. So essentially, what can you do with the rules that you've learned in the practice problems that you've done? Because on an exam, when you get a problem, you're not going to necessarily be given exactly what steps to do. It's going to ask you for some kind of value, and you have to figure out what to do to get to that value. So real quick, I just wanted to go over some background information that comes up a lot, especially in this video. So the first one, and probably the only one, is the number line trick. So the number line trick is where you take the derivative of a function. So here's the function I used, and then I found the derivative of it using the power rule, and that's the derivative function I got. And you'll probably recognize this, so you'll set it equal to 0, and find the solutions, the critical values, or the x values. So it can go by any of these names, but essentially you're going to find where x equals 0. And so for this function, the critical values and the solutions, or the x values, are x is plus and minus 4. So you would use this especially if you're only using the first derivative, you would use it to find areas where it's increasing or decreasing, or not concavity, that's second derivative, but you'd use it for concavity for the second derivative. So basically what you're going to do is you're going to put these numbers on a number line, right? So I put it -4 and 4 right there, and then you're going to pick a number left of the lowest number, and then right of the highest number, and then in between the two. And you really want these to be easy numbers to plug in, because you're not supposed to spend too much time on this. So 0 is a really easy one normally. And then usually you just have to go from there as to what the other two are going to be. And then, so the point of this is to see where it's increasing or decreasing, right? So that's talking about the slope, which means you're going to plug it into the derivative function. So I plug in my -5 into here, and I get a positive value. I plug in my 0 into this function, and I get a negative value. And I plug in +5 again into this function, and I get a positive value. So that just tells me that everywhere where I just got a positive value, the slope is increasing. And everywhere I got a negative value, the slope is decreasing. So from there, you can tell where it's increasing or decreasing. Now, if I found up here, if I found the second derivative, I could do all these same steps again, and I would find the concavity because I'm using the second derivative. So that was just the background information I wanted to give, because it'll come up a lot in the next points. So again, this is an applications review. So on the left side of the page, I put the first derivative. On the second side of the page, I put the second derivative. So essentially what I wanted to do was point out some of the parts that seem similar, but like the process is similar, but the names of them are different, and which derivative you use is the only difference really. So the first thing I want to talk about is critical points or critical values versus points of inflection and inflection points. So again, the first derivative function is on this side. So from the first derivative, you can get critical values and critical points. From the second derivative, you get your points of inflection. So the process you'll find is almost exactly the same. So the first step is to take the derivative of the given function for the first derivative, or for the critical points. The first step for the second derivative is to take the derivative twice, because you want the second derivative. The second step, however, you're going to set the functions you got from step 1 equal to 0. And then you're going to solve for x, or whatever the independent variable in your function is. Sometimes it's t, sometimes it's s, whatever it is in the function. And then you'll get the value that you're asked for. So if you solve for x after finding the first derivative and set it equal to 0, you're going to get your critical values. If you solve for x after setting the second derivative equal to 0, you're going to get inflection points. So that was the first one. Going through the rest of this video is kind of going to be very similar in terms of comparable steps and comparable outputs depending on which derivative you use. So the second one that I wanted to talk about, so for the first derivative, is it'll ask you where's the function increasing or decreasing, or describe the slope. Anything that has to do with the slope of the function is going to be with the first derivative. And then the comparable one to that for the second derivative is find where it's concave up or down, or describe the concavity of the function. So what's going to happen there is you're going to find the value we just found up here. You're going to start by finding that, okay? So for this one, for the increasing, decreasing, you want to find all the critical points. And for the concavity ones, you want to find the inflection points, because the critical points are the points where it switches from increasing to decreasing or decreasing to increasing. So basically it's where the derivative is 0. And then for the second derivative, the inflection points are where it switches concavity. So that point in the middle, like right here, where it switches from concave down to concave up, or from concave up to concave down, that point where it switches is the inflection point. So you want to find those. And then you're going to use the number line technique that we just talked about, but you're going to plug in the x values you get into the first derivative if you're finding increasing or decreasing, and then into the second derivative if you're finding concave up and down. So that's the part where it's different here. It's which derivative you plug it into. And then you'll get either a positive or negative value, same as the one in the example we just did. So if it's positive after you plug it into the first derivative, the function is increasing. If it's negative after you plug it into the first derivative, the function is decreasing. Over here, if it's positive after you plug it into the second derivative, that means the function is concave up. If it's negative after you plug it into the second derivative, that means it's concave down. So again, you can see there's a very small difference in terms of the procedure. And in this case, it's which derivative you turn it into, or you plug it into. Let's see. So there's going to be a question, almost guaranteed. There was one on every single class that I've tutored for that tells you to approximate the graphical representation of the function, or essentially just draw the function as best you can. And usually it's going to be a function that you can't really like do off the top of your head based on like pre-calc stuff like translations and stuff like that. So you're going to have to use, but mostly these two, definitely some of this up here too. So that's why I put it across the whole page. So I kind of just went through the whole process. So the first step is to find all of these points up here. So just follow these steps and find those points. The second step is to find where it's increasing or decreasing, so find these. And then where it's concave up or down, so find these points, or these ranges. So these are going to be ranges of values. These are just going to be individual values. So then you're going to plug in all of the critical points and the inflection points into the original function. So these points go into the original function. And the idea with that is you want to find exactly where the actual function is at these points. So you don't care about the slope anymore. You don't care about where it's facing or whether it's concave up or down. You care where the actual function is. And the only values we have, the only information we have about where the actual function is the original equation that we're given. So if we look back at the example from earlier, that would be plugging it into this function. So this is the derivative, this was the original function. And if you plug in a value for x, it'll tell you where the actual function is at that value of x. And that's why you want to do that. So again, you plug all of like the 2 points that you found up here into the original function. And then that'll tell you the exact location of those points on the graph. So then you want to tell where the max and mins are. We'll talk about that in a second. And then you use all the information you just found from these steps into the graph. So moving on to the next little step, that's really all you can do with the second derivative. So moving on, we'll pretty much only be talking about the first derivative. So another thing that they can ask is if you find, or they want you to find local maxes and mins, or find maxes and mins, or find the absolute max and min. So any version of maximum and minimums, you'll probably use these steps, and it'll definitely be with the first derivative. So again, you're going to find the critical points using the first derivative, set it equal to 0, solve for x. And then you're going to use the same number line technique, and then you're going to find where that function is increasing or decreasing. So all of these steps so far have been on the previous page we've already talked about. So then you're going to look at not only where it's increasing or decreasing, you want to see where it switches from increasing to decreasing or from decreasing to increasing. So picture that in your head, right? So if it's going from increasing, so the function values are getting higher to where they're getting lower, that's going to create a peak, and that's going to be a maximum. And then if you find where it's decreasing to where it's increasing, that's going to be a minimum. And again, just to double check which one is actually a maximum or a minimum, because sometimes you'll get one where it's going from decreasing to decreasing again. That won't be a maximum because it's still decreasing generally. So you only want it to be switching from decreasing to increasing or increasing to decreasing. So again, a quick way to double check, can you draw a straight line over the top of that? So you want to find where the derivative is 0. So boom and boom. But there's a distinction between all maxes and mins and absolute maxes and mins. So it kind of depends on how the question is worded in terms of the way you give your answer. So if the question asks, where are the maxes and mins? It wants you to know, or it wants you to tell where the x values of those maxes and mins are, because it doesn't care what they are, it's asking where they are. So all critical points where it changes from increasing to decreasing or decreasing to increasing. So it's just the x value if it asks you where it is. If it asks you what the maximum and minimum is, or asks you to find the maximum and minimums, it needs you to tell where it is and also what it is. So there's two separate ways to put that. You can either write it out, a maximum of the y value of that function at x equals blank. So what the maximum is and where it's at, or you can put a coordinate value. So you find, if it asks what it is, you find the y value of the function, or the y value of the coordinate, by plugging it into the original function, because again, you want to know where that maximum is, not anything about the slope. So if you plug it into the first derivative, that would be telling you information about the slope. You want information about the function, so you plug it into the original. And then I think this is the second to last one, but the last one we don't talk too much about in this video. So this one is absolute extrema. So same thing as maximum and minimums, but there's a difference between what is a max and what is the max. So this is essentially talking about what is the maximum value of the function. I'm sorry about my dog in the background. He's yelling at the mailman. So first step, find the critical points. Second step is use the number line technique. Third step is find where it's increasing and decreasing. Same thing so far. This step is the same as the last one, so find where the graph switches, whether it's increasing or decreasing. So same as last step. The new step is identify where, okay, so I guess this is technically the same as the last step. So you're going to see where it's a max and where it's a min, and then from those, you're going to plug all of those maxes and mins into the original function, right? So you're going to find the corresponding y value to those x's that were maxes and mins. Then what you're going to do is you're going to find the highest value among those that you plugged into the original and the lowest value. So the highest value will be the absolute maximum, and the lowest value will be the absolute minimum. And then the little caveat here is if the value goes to infinity, so if the graph goes like this, or yeah, so if it goes to infinity upwards, that's going to be a maximum of infinity. If it goes to infinity downwards, that's going to be a minimum of negative infinity. So that's the only little bit there, but usually they don't give you problems that really involve that kind of trick. And then the last little application of the first derivative is optimization, but there's a separate video about that one. So I'll leave it right there. Again, I will attach my email, so if you want a copy of these notes, the email will be in the description of this video, and I can just scan it and send you guys a PDF of it. But let me know, and good luck.